Welcome students once again into the class of topology, and we are continuing with the previous lecture that was based on the topic of filters. So let us see what the next theorems are, what the next definitions are, what the next fundamentals are. So the next theorem from where we are going to start today is that prove that arbitrary intersection of filters on a set X is also a filter. So we have to show that if we take arbitrary number of filters on a set X, then their intersection will also be a filter on the same set X. So let us start with the proof. Let X be a non-empty set, as there is no filter on an empty set, so we have to take non-empty set. So let X be a non-empty set. Let there be a family F lambda, where lambda belongs to a particular family lambda. Let this be arbitrary collection of filters on X. What we are to show that their intersection is also a filter on X. So let us name the intersection F lambda, where lambda belongs to that particular family, as F. Let this intersection be named as F. We have to show that this F is also a filter. That means we have to show the three conditions. That means phi does not belong to F. If a set F belongs to this intersection and it's a superset, then H must also be there in this set F. And if F and H are two members of F, their intersection will also be a member of F. So firstly, phi does not belong to F lambda for all lambda belonging to that particular family lambda, because every F lambda is a filter, and in a filter phi should not be there. And since phi is not there in any of these sets, that means phi is not there in the intersection of all these F lambda. That means F. So phi is not in F. The first condition is very clear, trivial. Let us move on to the second condition. Let F be a member of this F, this intersection. That means F belongs to the intersection F lambda. And since F is in the intersection, that means F belongs to F lambda for every lambda of that particular family. Let H be superset of F. Now F belongs to F lambda for every lambda, and this F lambda is the filter. In a filter, if F is there, then its superset H must also be there by definition of filter. So this means H belongs to F lambda for every lambda belonging to that particular family. And since H is in every F lambda, H must also be there in the intersection. So that means H belongs to intersection F lambda for that particular family, and this is your F. So if F belongs to F and H is a superset of F, then H also belongs to F. The second condition is also satisfied, and now we'll move on to the third and the final condition to show that this F, the intersection of this arbitrary family of filters, is also a filter. So third condition, let F and H be two members of this intersection of F lambda, where lambda belongs to that particular family. Now F and H belongs to this F, and what this F is, this is intersection of F lambda. Now F and H are in the intersection of this arbitrary family, so that means F and H are in every member of the family. So that means F, H belong to F lambda for every lambda belonging to that particular family. Now F and H are in F lambda, and what F lambda are? These are the filters. In a filter, we know that if two members are there, then their intersection must also be there. So this means F intersection H belongs to F lambda for every lambda in that particular family. Now F intersection H is in every member of this family. So since it is in every member, so it must be there in intersection. So this means F intersection H belongs to intersection F lambda for that particular family, and it is nothing but your F. So if you take two members F and H in the family, then their intersection is also there in the family, which makes this arbitrary intersection of filters another filter on the same